In this video, I'm going to talk about what are called post-hoc judgments. And so I've laid out here sort of a distinction between the availability heuristic, confirmation bias, and post-hoc judgments. So these are not in Steven Pinker's book. This is just sort of my way of kind of conceptualizing these things. And so the availability heuristic, which is what I talked about in the previous video, is sort of like our memory. So we have our memory here and say, in this box is everything we have in our memory. And then, some things are going to sort of loom larger in our memory while other things will loom smaller. And these larger things are things that will be more available to us. And so when we want to sort of call those forward in order to sort of make judgments, those things will be easier to find. Whereas confirmation bias, so once again, if this is sort of everything in our memory, confirmation bias is sort of everything outside our memory. So some things will be big, some things will be small. And so these big things are things that we will sort of notice more often. And so those will end up sort of going into our memory. And so confirmation bias in this way is sort of feeds our availability heuristic, sort of gives content for our availability heuristic. And so post hoc judgments are sort of confirmation bias in action. And so that's when we're sort of, looking out at the world and sort of, if we see something that looks, maybe just a little bit bigger than something else, our post hoc judgments will sort of blow this thing up so that it's much bigger while sort of shrinking this down so that it looks smaller. And so this is my sort of, broad conceptualization of these three things that often seem very highly related and maybe sometimes would seem like they're difficult to distinguish between. And so in this, I'll be talking about post hoc judgments, which, as I said, is sort of confirmation bias in action. And so it's very closely related with confirmation bias. And so post hoc judgments are sometimes called the Texas sharpshooter fallacy, where you essentially, shoot something like the side of a barn and then paint bullseyes around it, so that, no matter where you hit, you can sort of say that you hit the bullseye, that you got things right. And so post hoc judgments are when we count the times that something did happen, A, and ignore the times when it didn't happen, tilde A, or not A. And so you'll remember this is, pretty much exactly what I had in the availability heuristic video. But in that case, what I was saying is that our probability of A is sort of pulling from our memory. So pulling from our memory, where in this case it's sort of pulling from the real world or external world, so real or external. And so that's sort of the distinction between these two things, even though it's pretty much exactly the same thing in that what we're doing is sort of underestimating this these times when not A happens. So Steven Pinker actually gives this little example where if we think of like an investment advisor who has a 100,000 person mailing list, he sends a newsletter to half of them that the stock market will rise and the other half that it will fall. Then at the end of the quarter, whichever one of those was right, he keeps those people and drops the other ones, and then which is essentially keeping the hits and dropping the misses. And then he goes on to do the same thing, saying the stock market will rise to half of what is remaining, and stock market will fall to the other half that is remaining. And then once again dropping those who get the wrong information, keeping those who get the right information. And so then after, say, 2 years, so that's, 8 different cutting in half of his people, but he'll be left with just 1,562 people, but those will be people who only ever got right predictions for the last 8 quarters, and so these people think this guy's a genius, and the guy can sort of make himself look like a genius. He can sort of bring people from these 1,500 out and have them sort of sing his praises, so that maybe he even gets awarded some kind of award for being such a great investment advisor. And so that's kind of what we're doing with these post hoc judgments, is sort of just keeping the times when we're right and sort of ignoring the times when we are wrong. So another place where post hoc thinking can lead us astray is with the frequency of coincidences. And so people can easily remember the sort of spooky coincidences that happen, which is A. But when there is no coincidence, so not A, then there's nothing to even remember. Non-coincidences are constantly happening all the time, but we don't notice them as non-coincidences because there's nothing sort of noteworthy there. And so these non-coincidences don't actually get included sort of in our denominator. So this will be much smaller, and therefore our prediction, or sort of our judgment that this coincidence is, something sort of noteworthy, will seem much bigger. So this is kind of one of the famous ones here. So the strange coincidences between Abe Lincoln and John F. Kennedy, who were both assassinated. And so, it shows like when both of them were elected, it was like 100 years apart, and, all these different things, which seem, like sort of spooky coincidences. Though, if I'm not mistaken, I think that some of these are actually not even true. For instance, this one here will advise not to go by a secondary named Kennedy. I think maybe a few of these are made up. But even if all of them were true, it's one of those things where it's like, wow, isn't that spooky? These strange coincidences. But all the times where there are not coincidences, even between these two people, look at we look at this and see, wow, that looks like a lot of things. That looks like a lot of different coincidences. But we're also not looking at, the huge amount of non-coincidences that you would find between those two people. And so I recommend this video here by Vsauce. So this is the thumbnail for that. And so it's actually called Spooky Coincidences. And so he actually talks a bit about this presidential one, and numerous other types of sort of spooky coincidences, and sort of goes into how you would expect coincidences like this to happen sometimes, and how we don't pay attention to any of the sort of non-coincidences, which would vastly outnumber all of the things that are coincidences. And so this is where that post hoc thinking can lead us astray. Like I said, it's sort of underestimating this not A here, because we're not noticing all of the non-coincidences happening. So and I said this is another type of post hoc thinking, and they're kind of similar, but it's called the cluster illusion. And so we see here this chart of randomly generated crosses on here. But if you're looking at this, you're probably going to think like, oh, look at this, there's a little cluster right here, and there's this cluster here, and this could be a cluster too, and look at this cluster here and this cluster here, and you could go through finding all these instances of clusters. And so it's a set of 100 randomly generated coordinates, and I got this from Wikipedia. Displayed on a scatter graph. Examining the points is easy to identify apparent patterns. In particular, random data points do not spread out but cluster. And so if something is truly random, you will expect to find clusters. But when humans look at something that's randomly generated, we see or we get the impression that there are hot spots. And, because humans like to sort of think causally, we sort of guess that there must be some kind of underlying cause. And it's the same with the coincidences, where these coincidences would be sort of like clusters that show up in sort of the random data of history. And so we can pick out those weird little clusters of coincidences, and like to we like to ascribe some kind of underlying cause to those things. And so the cluster illusion can show up in coin flips as well. So Steven Pinker says that even statisticians, when shown real data, and I copied these things right out of his book. So when shown real data like this one up here, even statisticians oftentimes think that the coin must be rigged because there are too many tails at the end. So we see this cluster of tails here at the end. Then when shown fake data like this one, people think that this appears more random because it lacks the clusters that actually do show up within a series of random events. And so I took this from Wikipedia here. So this is talking about sort of using the p-test, or the p-value, to actually sort of test the hypothesis that a coin is unfair. And so to sort of summarize what this block of text is talking about, it's saying that we're saying that essentially the probability that, say, the number of heads is greater than or equal to 14 given the null hypothesis, where the null hypothesis would just be that if you flip, so we're flipping the coin 20 times, so we flip 20 times, and the null hypothesis would be that you would get 10 heads, because we're saying that it's 50-50, so the null hypothesis is 10 heads. And so this is saying what is the probability of getting greater than or equal to 14 given that the null hypothesis is 10 heads. And so what we can do, so it actually goes through it down here. So the coin is flipped 20 times and comes up heads 14 times. Is the coin fair? And so we see here the null hypothesis that the coin is fair, that the probability of heads is equal to 0.5. And so we want an alpha level, which is 0.05 or lower. So if you've read like scientific papers, you may have seen the p values where they want a p that's lower than 0.05. That 0.05 is telling you that that there's like less than sort of a percent chance that this would happen on accident. That, say, getting heads 14 times would happen on accident. And so we're doing a two-tailed p-value. So the tail it's talking about is, say, this tail up here or this tail down here. And so it's saying that that right in the center here is 50-50, so 10 heads and 10 tails. And then, it's saying that this point right here would be like getting 14 heads, or I guess 14 tails, if the case may be. And so something that would seem unusual. And so we note, well, let's skip ahead here. Here we calculated a p-value that exceeds 0.05. So this was the p-value that was calculated here, meaning that the data falls within the range of what would happen 95% of the time. And so we're saying that 95% of the time, so the data between this point here and like this point here contains 95% of the times. And so you flip a coin 20 times, and then you do 20 flip trials 100 times. It's saying that within 95 of those, you would get some heads greater than or equal to 14. So here we're looking at equal to 14 because we want the observation to be 14 heads. Because if it's greater than, as we'll see, then it would actually be, outside. It would say that this is something unusual. So by getting this p-value of 0.115, which is greater than 0.05, it's saying that this 14 heads is something that we would expect, given that this is a fair coin. Just by probability, that if we have this null hypothesis of 10 heads, we would still expect within sort of 95% confidence that we would sometimes get 14 heads out of our 20 flips. So here it says, however, had one more head been obtained, then the resulting p-value would be 0.0414, which is less than 0.05, in which case the null hypothesis would be rejected. So in other words, that would tell us that there is something funny about this coin. So if we get 15 out of 20 heads, that's telling us that this is sort of that there is, sort of an underlying cause here. So an underlying cause here. So maybe the coin is not it's not a fair coin. So that would be sort of an underlying cause where when we only got 14 heads out of 20 flips, this is telling us that there is nothing funny about the coin, that the coin is in fact a fair coin. And so getting 14 heads out of 20 flips is something that you would sort of expect. And so the p value thing, it's 0.05 is kind of the standard in a lot of scientific papers, that being less than 0.05 means that there is a sort of statistical significance. And you can get into sort of the statistics and sort of the sort of meta science, I guess you could call it, about whether 0.05 is good enough, or if it should be more than that, or what criteria tells us that 0.05 is good enough. And you maybe have also heard of things like p hacking, and so that would be, if you got like this result here that said that there's nothing interesting, p hacking might be like, well, let's do like a few more trials, and maybe some of those will have outliers enough that we actually go into the statistical significance, and therefore that means that our experiment showed something interesting. Or another thing that you might end up doing is sort of throwing out data that you could maybe sort of post hoc say was spurious data, and by throwing out that data you can sort of get yourself to a p below 0.05 and therefore make it look interesting. And so that is one of those things that has been found in the sciences, and particularly social sciences, that this p hacking can oftentimes be an issue. And so I think it was during like the last 20 years or so that like a lot of scientific studies have sort of come under scrutiny for this sort of p hacking type stuff, especially, like I said, in the social sciences. And so this whole thing about like the p value and p hacking could probably be made into an entire video playlist, all on its own. So I'm not going to get too much into it here, and I don't want to get bogged down in the math too much. But the take-home message for this part is just that this p less than 0.05 is telling us that there is like a less than 5% chance that the result we got was sort of just by statistical accident. That there's less than 5% chance that the result we got was something that you would just expect from sort of random or probabilistic fluctuations around the mean of, your 10 heads out of 20. And so this is saying that 14 heads is not statistically significant. You would have a greater than 5% chance of sort of finding that result, where if we added one more and got to 15 heads, then we would say that that is statistically significant and that it therefore is something that we would not expect from just sort of random fluctuations. But anyway, I don't want to belabor this point too much. So another couple things that we could think of as sort of clusters is so the stars making constellations. And so that's one of those things that you sort of see patterns in the randomness or patterns in the noise, seeing that stars making these certain shapes in the sky. And so the other one is the fact that if 23 people are in a room, so 23 random people in a room, that 2 will share a birthday is greater than 50%. And so you can actually see the number of people in the room here. So once you get up to, like 70 people in a room, there's like a 100% chance that at least 2 of them will share a birthday. But anyway, that is everything for this video. So that is on post-hoc judgments. So in the next few videos after this, which is moving on to the next chapter in Steven Pinker's book, is going to be about sort of Bayesian thinking and Bayesian reading. And so we're still going to be using a lot of these ideas from probability, since Bayes' theorem is a theorem in probability theory. But it's sort of a way of thinking probabilistically that humans both are good at in some instances, but also bad at in other instances. And we will see how that works in the next few videos. So I hope you found this video helpful, and I will see you in the next one.